Let's jump right into this explainer and unpack an absolutely incredible mystery of human engineering from back in 2010. We're talking about a story of sudden natural disaster, immense physical forces, and the honestly fascinating ways that science allows us to, well, literally build a defense against the unpredictable. So picture this. It's February 27th, 2010, and a massive earthquake strikes right off the coast of Chile. We're talking an 8.8 magnitude event here. Just to put that into perspective for a second, this quake was so incredibly powerful that it violently shook buildings, caused massive bridges to sway, and actually shifted the solid ground itself by several meters in some areas. It was just a terrifying display of the Earth's raw power. But here is where it gets really interesting. If we look at the stark contrast between two major seismic events that same year, it's pretty mind-blowing. A devastating earthquake struck Haiti with tragic consequences. Yet, the Chile quake actually released roughly 500 times more energy than the Haiti earthquake. Let that sink in. 500 times. But despite that absolutely staggering difference in sheer destructive power, Chile's death toll was vastly lower. So that brings us to the million-dollar question. Why exactly did those buildings in Chile stay standing? How on earth does a society engineer its way through an 8.8 magnitude seismic event? Well, as you'll see, the answer isn't hiding in just one science textbook. It requires a really unique, interdisciplinary approach, stitching together entirely different fields of science to solve a high-stakes, real-world problem. To solve this mystery today, we're going to use a roadmap that combines knowledge from earth science, physics, chemistry, and life science before putting it all together in a final real-world test. So let's start right at the source with earth science to understand the tremors themselves. To understand where and why these massive earthquakes even happen, you have to look beneath the surface. Chile sits right on what we call a convergent boundary. This is exactly where the oceanic Nazca Plate is actively subducting, or basically diving right beneath the South American plate down into the Earth's mantle. And as this happens, enormous, almost unimaginable stress builds up along that fault line. Eventually, that pent-up stress actually exceeds the physical strength of the rock itself. And when that happens, boom, the plates violently slip. That violent slip releases all that stored energy as seismic waves that radiate outward. And engineers absolutely have to understand how each type of wave directs forces onto a structure. You've got three main culprits here. P waves, which essentially compress and stretch the ground in the direction they're traveling. Then S waves, which shake the ground violently from side to side. And finally, surface waves, which combine both of those motions and, as you might guess, typically cause the most catastrophic damage. Because if you don't know the exact character of these waves, you can't possibly know how your building is going to be attacked.
But knowing exactly how the ground is going to shake is really only step one. Step two brings us into the realm of physics, where we actually fight those forces.
Now, Isaac Newton wasn't an architect, right? But his laws totally dictate whether a building survives or not. Take Newton's first law of motion, inertia. Imagine a massive high-rise. When those seismic waves hit, the ground suddenly jolts, but the massive weight of the building naturally wants to resist that change in motion. So as the base of the building accelerates horizontally with the moving ground, the upper floors basically try to just stay in place. This creates a terrifying net force, a real whipping action that can violently twist, bend, and ultimately snap the entire structure. To combat this, engineers pull Newton's second law out of the playbook. Force equals mass times acceleration. Since the force on the building depends on its mass and the ground's acceleration, they tackle both variables head-on. First, they reduce the mass by using lighter materials, which immediately drops the total force. Second, they reduce the acceleration transmitted to the building using these completely ingenious base isolation systems. Think of massive rubber and steel pads tucked right between the building and its foundation. They essentially allow the violently shaking ground to just slide right beneath the building, keeping the upper structure relatively still. It's brilliant. And of course, we can't forget Newton's third law. For every action, there is an equal and opposite reaction. To visualize this in action, you just have to look at Taipei 101 in Taiwan, which sits right in a massive earthquake zone. Engineers there installed a staggering 730-ton steel pendulum called a tuned mass damper near the very top of the skyscraper. When seismic forces push the building one way, conservation of momentum dictates that this massive pendulum swings in the exact opposite direction. It literally fights the quake to keep the skyscraper perfectly stable. It's just an absolutely gorgeous application of physics. Okay, so forces are one thing, but what about the actual stuff the building is made of? That brings us to chemistry, and specifically materials that flex. It's incredible to think about, but the very atomic bonds of these building materials are what dictate survival. At the microscopic atomic level, the contrast is just fascinating. Unreinforced concrete and standard brick rely on ionic or covalent bonds. Sure, they are fantastic at supporting heavy, static weight, what we call compression, but they're incredibly brittle. When twisted by seismic forces, those bonds simply crack and the material crumbles. Steel, on the other hand, features metallic bonding. This creates a literal sea of electrons, positively charged metal ions surrounded by these delocalized, free-floating electrons. This unique atomic structure makes steel highly ductile, so it can stretch, bend, and deform elastically during a quake, instead of just shattering. So what did the clever engineers do? They combine them. Modern earthquake resistance relies heavily on reinforced concrete, which beautifully marries the two chemical properties we just talked about. The concrete easily handles the immense downward compression of the building's weight, while the embedded steel bars, the rebar, flex to handle the violent side-to-side tension and bending forces of the earthquake. Their atomic structures literally complete each other. All right, so we've built our resilient, flexible structure, but the ultimate purpose behind all of this brings us to life science, because the real goal here is protecting the people inside.
You see, keeping the building upright is really only half the battle. To truly protect human life, engineers have to understand the biological hierarchy of the human body. Biologically, we are organized from very delicate cells up to tissues, to organs, and finally to whole organ systems. When a building shakes violently, physical trauma can cascade through this entire chain. Obviously, a collapsing structure can crush bone and tissue. But here's the kicker. Even if the building stays perfectly intact, the sheer movement itself can be insanely dangerous. Just look at one specific, highly critical organ, your brain. Our brains are incredibly delicate neural tissues suspended in cerebrospinal fluid inside the hard bone of our skulls. Even without a building collapsing, sudden, violent acceleration or rapid deceleration can cause severe internal injuries. The brain can literally collide with the inside wall of the skull, causing massive concussions or even worse. This is exactly why building codes strictly dictate the maximum allowable sway or interstory drift. The building isn't just designed to stay up, it's designed around our strict biological tolerances so the humans inside aren't subjected to lethal G-forces. So, bringing this all together into the real world. As we saw with those incredible buildings in Chile back in 2010, this entire explainer really highlights that no single branch of science can solve complex, high-stakes problems all on its own. The most effective scientists and engineers out there, they think across disciplines. So I want to leave you with this provocative thought experiment. If you were the lead engineer tasked with designing a critical hospital in a massive earthquake zone, a building that absolutely must remain operational to treat the injured, how would you synthesize earth science, physics, chemistry, and life science to keep your patients safe? Think about the seismic waves, those clever base isolators, the sea of electrons in the steel, and the fragile biology of the patients. What specific decisions would you make? Keep that in mind next time you look at the towering structures around you. Thanks for joining me on this explainer, and keep questioning the science behind our world.